And good afternoon, fellow mathematicians. And today we are going to solve another integral which involves Gaussian integral and Feynman technique and the complex analysis. Well, the integral we have here is I equals to 0 to infinite sine 2 ln square x over 1 plus x ln square x dx. First of all, we need to separate the integral like 0 to 1 plus 1 to infinite and the required part. And by taking that required part, let's take that as I1, and what we'll have here is I1 equals to 1 to infinite sine 2 ln square x over 1 plus x times ln square x dx. Now if we do some substitution, we'll get x tends to 1 over x, and we'll get the dx becomes 1 over x square times dx, and the boundaries will become, when we apply 1 it will become 1 and the infinite becomes 0, and what we'll have here is I1 equals to 0 to 1, and this minus will come here and change the boundary, so don't worry about that. And what we'll have here is sine 2 ln square 1 over x over 1 plus 1 over x and ln square 1 over x times 1 over x square dx. And by doing some simplifications here, we'll get the integral become 0 to 1 sine, terribly sorry about that, we'll get sine 2 ln square x again and 1 plus x times ln square x, and we'll have an extra x here, and don't forget the dx. So this is what we have for the I1 part. Now let's take the I integral, which is 0 to 1 sine, terribly sorry about that again, we'll have sine 2 ln square x over 1 plus x times ln square x dx plus this I1, which is 0 to 1 sine 2 ln square x over 1 plus x ln square x dx. And we can see that clearly now. We can write this integral as 0 to 1 sine 2 ln square x over 1 plus x ln square x times, and we'll have x plus 1 over x dx. Well, eventually this one and this one will cancel each other out, and we are finally left with the required integral will be 0 to 1 sine 2 ln square x over x times ln square x dx. Okay, cool. So now let's take the substitution, which part ln x is equals to t. So differentiating both sides with respect to x, we'll get 1 over x dx equals to dt. And the boundaries will become, when applying 0, we'll get, it will become minus infinite, and by applying 1, it tends to 0. So now the integral will look like this, which is I equals to 0 to 1 sine 2t square over, take the t square out, and we are finally left with 1 over x. We can put 1 over x as dt, and that's it. Now this is where the part we are going to do some Feynman trick here. Let's take I of alpha, which is equals to 0 to 1 sine alpha t square over t square dt. Well, when alpha is equals to 2, the required integral will be the I, and I of 0 is just 0. So when differentiating both sides with respect to alpha, we'll get 0 to 1, we are finally left with cosine alpha t square dt. And here we go. Now this is where the part we are going to do some complex analysis part. We know that e to the I alpha t square is cosine alpha t square plus I sine alpha t square. Well, this is actually the real part of e to I alpha t square. So we can write this as I prime of alpha is equals to 0 to 1, the real part of e to the I alpha t square and dt. So we know that Gaussian integral is 0 to infinite e to the negative a x square dx is half times pi over a. By looking these two, they both similar, so we'll get an answer which is I equals to, which is I prime of alpha is equals to the real part of half times pi over I alpha, because we are integrating with respect to t here. So what is the real part of this complex number? We can take the half outside and even the pi of alpha too, but inside we'll get real part of I to the negative half. And here we go, what we have here is half pi over alpha and the real part of I to the negative half. Well, we know that I is actually cosine pi by 2 plus I sine pi by 2. And we want that minus half here. And once again, we can use some de Moivre's theorem here, which is we can multiply this half here. So we'll get cosine minus pi by 4 plus I sine minus pi by 4. And only by taking the real part, we'll have I prime of alpha is equals to half pi over alpha, and real part of it is equals to cosine pi by 4. We don't have to worry about that minus because it's cosine. So what we'll have here is cosine pi by 4 is 1 over root 2. So what we'll have here is half times pi by 2, and I'm going to take that alpha outside. So now integrating both sides with respect to alpha, we get the required integral, which is I of alpha half pi over 2, and with respect to alpha we get and another half, which eventually and this part will cancel each other out, and with the required integral will become, which is pi alpha by 2 plus, don't forget the c. We know that I of 0 is actually 0, so when plugging we'll get c is equals to 0. So I of alpha is actually now will become pi alpha over 2, and we know that when alpha is equals to 2 we'll get the required integral, which is I of 2 is actually I, so the required integral will become times 2, and what we'll have here is the final answer root pi, which is an incredibly awesome answer. And okay guys, and that's it for today, and we'll find some other integral using other techniques, and until then, bye bye from your boy Abhi. Thank you, and don't forget to hit the subscribe button.